Thank you very much. Thank you very much for the invitation and for the introduction. And sorry once again for the mess. Let me just try to get started so that we don't waste more time. So I'm going to start by setting up the notation and giving a little bit of motivation for what I'm going to say. So we're going to consider a collection of S points in general position in projective space. I'm going to work over the complex numbers. And then we consider the blow up of the projective space, this collection of points, and we call EI the exceptional divisor of a point PI. And now we want to sort of give a basis for the Picard group of this space. And so we're gonna say that the Picard group is generated by the exceptional divisors, and I have S of them, and then by the class H of a general hyperplane. So it's just a pullback of O of 1 from Pn. So we're going to be able to consider divisors in this space, and in particular, we are going to define divisors that we call D as given as this linear combination. We take D times H, and then we subtract every exceptional divisor a number of times, Mi, Ei. And so that's I'm using this minus here instead of a plus because I want to somehow connect the linear system associated with this divisor with something that's somehow the vector space of homogeneous polynomials of degree D that vanish with multiplicity at least Mi at the points Pi. So it's somehow what we can call polynomial interpolation problem to ask how many of these polynomials do we have. And since there is up to multiplication by scalars, there is a one-to-one correspondence between such hypersurfaces of degree D with points of multiplicity Mi and the linear system of divisors D defined this way. The question, how many such hypersurfaces do I have, which is what we call polynomial interpolation problem, is answered simply by the computation of the dimension of the space of global sections of the sheaf associated with this divisor D. So I'm going to abbreviate with H0 of D in the next slides. But there is also, there is also another related question, that is how many unexpected hypersurfaces do I have? Because, of course, one can do a parameter count and come up with an expectation for what is the answer to this problem, but this expectation is not always met. And somehow a measure of how many unexpected such hypersurfaces is encoded in the dimension of the first cohomology group. And in order to justify somehow this claim, I am gonna be a little bit more specific on what is the expectation. So we call the virtual dimension of D, of the linear system associated with D, we call it virtual dimension, the Euler characteristic of the sheaf -1. And that is, well, with a little bit of calculation, not much, one can see that this equals the following number. So I take this Newton binomial, n plus D, choose D, which is the number of homogeneous polynomials of degree D in n+1 variables. So the number of hypersurfaces of degree D of the n-dimensional projective space. But then I'm imposing some singularities. So for each point, and I have S of them, I'm imposing this number of conditions that correspond to the vanishing of this number of partial derivatives of order Mi-1. And then, that will give me somehow a fine dimension that I'm interested in, projective dimension, the dimension of a linear system. So I subtract a 1 there. So this is the virtual dimension, and then we can say that if the dimension of the linear system, or in other terms, if the number of global sections of the sheaf equals the Euler characteristic, then we say that D is, we call it non-special. So it doesn't have a special behavior. It behaves like expected. And the second observation, as I said, is that, the measure of the spatiality of the linear system is encoded in the first cohomology group, H1. And why is that? Well, one can show that the Euler characteristic equals, so usually this is the alternating sum of all the cohomologies, but the only two that might not vanish are H0 and H1. Everyone else vanishes. Hi of D is equal to 0 for every I from 2 and on. So these are the only two numbers that we are interested in, and one of them computes the number of such expected hypersurfaces, and the other one counts the number of unexpected ones. Yeah, so we will say that this is somehow a measure of speciality. So how do we approach this problem, the problem of computing either this number or that number? It's equivalent because we know the Euler characteristic. Well, the philosophy is to look at the base locus of the linear system. So if the base locus is empty, which in other terms mean if the this vector space of hypersurfaces in the projective space have singular points only along the, well, it only has the imposed singularity and nothing else, then in that case we expect that the linear system is non-special. So we expect to find no unexpected hypersurfaces. Whereas when the base locus is not empty, so if there's something else, then it might or might not be special. When it's special, we talk about special effect subvariety to define the varieties that are contained in the base locus of this linear system. So, and the question is, can we say when it actually is special, and can we describe this special effect subvariety and even, you know, determine how much they contribute to the speciality of the linear system? So we're going to look at a few easy examples just to have an idea of what I'm talking about. So now we're taking examples in P2, so in the blow up of P2 at a collection of points. And we consider, for instance, this divisor. So these are sextic curves. These are plane curves of degree 6 with 2 points with assigned multiplicity 4. And what is written here on the right-hand side is the Zariski decomposition of this divisor, where this is the fixed part, because you can see this is h minus 1 minus 2. This is the class of a line through 2 points, so it's a fixed divisor on the blown up plane, and this is the nav part. So if we do the computation that we have learned how to do in the previous slide, so if we compute the Euler characteristic of this guy, let me call this divisor D. The Euler characteristic is, well, it's 8. I've done the computation. But there is a fixed component, so there is a line that splits off twice the linear system, and this is the moving part, the nav part. So this is quartic curves with 2 double points. So the dimension of D, the number of global sections of D, corresponds with the number of global sections of the nav part, and this one can compute that is equal to 9. So there is a gap between expected dimension and actual dimension. So in other terms, H1 of D is 1. So in this case, the system is special. And similarly, I'm going to consider a second example, which is very similar, and I'm just going to increase by 1 all the parameters. So degree 7 and 2 points of multiplicity 5. In this case, it's easy to see that the same line as before, splits off 3 times. And the nav part is the same. So in this case, the Euler characteristic is 6. The number of global sections is again 9, because, well, the moving part is the same. So also in this case, the linear system is special, and the speciality is a little bit larger, is 3. So you see it grows as the multiplicity of the base locus component grows. And so we will call, this that we're looking at is what we call a special effect line. So a line through 2 points is a special effect variety. Also, a conic through 5 points is a special effect variety. And, well, we can give as many examples as we want, but the easiest one is to consider quartic curves with 5 double points in general position. We expect that there's no one in that, so that the Euler characteristic is 0, but in fact there is one element that is the double conic. So also in this case, the speciality is equal to 1. So we have also, we have sort of somehow identified another curve that is a special effect. So that's a conic through 5 points. Not all curves that are sort of multiple components of the base locus are special effect, because for instance, if we consider this last example, these are curves of degree 6 with 9 double points, that one can show easily that there's only one such element, a non-reduced element, that is twice the cubic. There is a unique cubic through 9 points, and if I take that twice with multiplicity 2, turns out to be the only element in here. But in this case, the speciality is 0, so a double cubic curve is not special effect. So the remark that we make here is that the two special effect curves that we found, they are both rational, a line and a conic, and they are somehow, because I'm looking at them in the blown up space, they are both -1 curves. They are -1 curves that, well, that means irreducible, rational, with self-intersection -1, and well, one can compute that they intersect the canonical divisor. The intersection with the canonical divisor is -1, but that follows from Riemann-Roch somehow, whereas the cubic is not a -1 curve. In fact, it's an elliptic curve, it's not rational, and it's not a special effect variety. So one wonders whether it is the case that only -1 curves sort of are interesting for our purpose. And this is actually a conjecture well, with 4 names, but the first name that appears here is Segre, Beniamino Segre, and then 3 more people. I mean, this conjecture was like formulated over a century, basically, but the first idea goes back to Segre, and the other 3 are Harborn, Gimigliano, and Hirschowitz. And the conjecture is that special effect curves, so this is a conjecture for P2 blown up at points, special effect curves for non-empty linear systems, or for linear systems of effective divisors on the blow up, are all and only the -1 curves, whenever contained at least twice in the base locus. And we have seen a few examples. So this is a conjecture. Actually, one implication is easy, so that if there is a -1 curve, a non-reduced -1 curve in the base locus, then the linear system is special. That's easy to show. It's the other implication that is the content of this conjecture. And this conjecture was proved to be true by Castelnuovo for up to 9 points, on P2. And why 9? Well, so for sure, up to 8 points, there are finitely many -1 curves. And well, if I blow up P2 up to 8 points, I get a del Pezzo surface. I have a Fano surface. It has a finitely generated effective cone. It's actually generated by the -1 curves. There are finitely many of them. If I blow up an extra point, this is no longer a del Pezzo surface, and in particular, there are infinitely many -1 curves, but nevertheless, Castelnuovo managed to show that even if you have to deal with infinitely many potential special effect curves, you do get a proof of this conjecture, and that is because I guess the content of the proof, well, the idea of the proof says that even though I have potentially infinitely many -1 curves, I cannot have infinitely many of them in the base locus of an effective linear system, because if I do, then the linear system is empty. There is no such section in there. So somehow for S equals 9, somehow the proof goes into the direction of showing when a linear system is empty rather than when a linear system is effective and what is the dimension. And just to mention here, there is another conjecture that is related to emptiness of linear system, and this is also wide open, and that's due to Nagata. So while he was doing something else, he was constructing a counterexample to Hilbert's 14th problem, and while doing that, he proved some result about emptiness of plane curved linear systems, and then he conjectured that the behavior of the examples he looked at should be general. So this is the statement. So if I have at least 9 points, as long as I have this bound, so that means the points are many respect to the degree and the multiplicity, then the linear system is supposed to be empty. So somehow these two conjectures are related, but today I'm going to mainly focus on the first one, and actually I'm going to try to sort of generalize Castelnuovo's proof of the conjecture to the higher dimensional case, so linear systems in higher dimensional space. But yeah, so sorry. So what I was, so I mentioned that if I have a limited number of points, then the blow up is Fano, is at the Pezzo, so it's Fano, so it's well behaved from the birational point of view somehow, and I managed to understand everything. And but if I go to the next step, so if I consider higher dimensional cases, I do have a classification of what blow-ups behave well from the point of view, from the birational point of view. And this is due to Mukai and Kastravet-Tevelev, and they give a complete classification of what blow-ups of projective space in points in general position are Mori ring space. So that means which of them have finitely generated Cox ring. That's one way to define that. And we have a list, and the list is in dimension 2, we have the Pezzo surfaces, so up to dimension 8. And in dimension 3, we can blow up to 7 points, up to 8 points in dimension 4, and in general, up to n plus 3 points, where n is the dimension. So this is the list. And from the, let me say, from the dimensionality point of view, so dimension of linear systems in there, what do we know? Well, the case of the Pezzo is solved by Castelnuovo. And we will talk today about, we're going to talk about the second and the last case. Whereas there is one case that is still missing, the 4-dimensional case with 8 points. And yeah, I'm just going to say this is in progress by Santana Sánchez. I guess he's on his way to finding a solution, but well, still working on it. Okay, so but yeah, so I'm gonna, as I said, I'm gonna talk about this 3-dimensional case or the n-dimensional case with a limited number of points. But before going there, I'm just gonna look more closely at Castelnuovo's result, and then I'm gonna generalize somehow the ideas that are in there to the other higher dimensional case. So again, we go back to the Del Pezzo surface case. So we take blow up of P2 at up to 8 points, and we consider this theorem by Castelnuovo. So he shows that, well, given a linear system like this, so that's in P2, the number of global section equals the Euler characteristic plus a correction term. So this is going to be the H1 of D. And that's a summation where we have these Newton binomials. And I'm going to say what this is. So the summation is over the -1 curves. So C is going to be a -1 curve. And for each -1 curve, we need to know what is the multiplicity of containment in the fixed locus of D. So in other terms, how many times does a given -1 curve split off the linear system of D, like we've seen in the previous examples where we had the line or the conic splitting off. So this number can be computed. So yeah, I think it's enough to say that. So that's the multiplicity of containment of C in the base locus of D. And it's also, this number is computed very easily. So we just take the intersection, the negative of the intersection number between C and D. And if this number is negative, I don't consider it. if it's positive, that's going to be my multiplicity of continuum. So that's something that is possible to prove, and that certainly Castelnuovo did prove. So -1 curves are responsible for the speciality of plane linear systems. Moreover, they have some other geometric meaning, in the sense that they generate the effective cone. In this case, I'm talking about the Del Pezzo case. And another thing that is, very interesting is that they are related to one another by a sequence of Cremona transformations, whatever that means. But somehow the good thing about it is that once you find one of them, then you find them all, because you can, apply these Cremona transformations to come up with a complete list. So let me remind you what is a Cremona transformation, standard Cremona involution of P2. So this is simply this birational map from P2 to itself, and that is defined by sending the point with coordinate x0, x1, x2 to the point with the coordinates or the inverses, x0, -1, etc. So in other terms, how does that work? So we want to see how does this transformation acts on -1 curves. So what does it do? So let's consider the drawing. We do a drawing here. So we take P2, and here I'm drawing a triangle of lines. I'm assuming these are the lines along which this map is not determined. So this is the indeterminacy locus. So I have 3 coordinate lines and 3 coordinate points. Let me call them P1, P2, P3. So what do? Well, I blow up, I resolve this indeterminacy locus, and by doing that, I obtain an hexagon of curves where the red ones are the exceptional divisors, E1, E2, E3, and the blue ones are, well, the strict transforms of the 3 coordinate lines. And then I blow down, so this is blow up the points, and here I blow down, contract the lines. Let me call them Lij. So this is the strict transform of a line through the point Pi and Pj. So I contract them and I obtain another triangle, this time upside down. And in some sense I have, so this is somehow how to visualize this Cremona involution, and what I've done, I have swapped points with lines, basically. So this is the idea, so how to understand it. But what I want to do is I want to see how this transformation acts on curves in general. So if I have, well, clearly what it does to the exceptional divisors, it takes an exceptional divisor to a line and vice versa. But if I have a general line, let's say, well, let me take another color. I'll take a general line, it will intersect the 3 coordinate lines and it will not go through the 3 coordinate points. So if I blow up and then blow down, where does this line go? Well, it intersected the three coordinate lines, and therefore when I do this operation, then it will go through the 3 coordinate points on the other side. So it becomes a conic through the 3 points. So a general line becomes a conic through 3 points. And if I want to describe this in coordinate, I'm going to do it here. So I'm going to write in coordinate what the Cremona involution, how the Cremona involution lifts to an automorphism of the Picard group of the blow up of P2 in 3 points, or more generally, the blow up of P2 in S points. I can extend by linearity. So I see how it acts on the Picard group. So I take this map. So we said a general line that I denote by H goes into a conic through 3 points. E1, E2, E3, the 3 blown up points. The exceptional divisor EI goes to the line. So I'm assuming that now I, J, and K, I take 3 distinct indices equal to 1, 2, 3, like a permutation of 1, 2, and 3. So the exceptional divisor EI goes to the line through Ej to Pj and Pk, so through the class H minus Ej minus Ek, and the exceptional divisor Ej, where J does not belong to 1, 2, and 3, so it's not somehow in the among the 3 points where I base my Cremona transformation, that goes to itself. So this defines an action of the, these Cremona transformations on the Picard group. And I can keep applying these Cremona transformations by choosing different points, to base the Cremona transformation on. And I can keep doing that. And then one can see, I will say a little bit better later, one can see that the action is transitive. There's only one orbit, and that up to 8 points, I have a finite orbit. And when I have at least 9 points, the orbit is still unique, but it has infinite elements. And the elements are, So if I start from a -1 curve and I let these Cremona transformations act, I will obtain another -1 curve, etc. So they will all be in the same orbit. How to say? So this is for P2, but the same identical thing happens in Pn. So it's easy to imagine how this standard Cremona transformation is defined in Pn. Simply add more variables. And the action on the Picard group is similar, so it is written here. So I send the class of a general hyperplane H to the class of a hypersurface of degree n through n+1 points with multiplicity n-1. So if you replace n with 2, then you get a line through 2 points, like in the previous slide. And it sends exceptional divisors to hyperplanes through n points. So and then so the action is completely similar, and we call Weyl group, and the notation is W and S, where n is the dimension of the ambient space and S is the number of points that I blow up. So we call the Weyl group that acts on the Picard group the group generated by the standard Cremona involutions with the operation of composition. So that's what I was saying earlier. So this is how to extend somehow this notion of Cremona transformation in higher dimension. And but now thinking back to Castelnuovo's result, I need to tell what are the -1 curves in higher dimension. What does it mean, -1 divisor in higher dimension, or -1 cycle in general? What does it mean? So that's what we are gonna look at now. So first of all, we need to define sort of an intersection pairing between divisors, and that that was introduced by Dolgachev and used by Mukai. So it's a bilinear pairing on the Picard group, and it's a diagonal. It has a diagonal matrix. So if I intersect a hyperplane with another hyperplane, I get n-1. If I intersect a hyperplane with an exceptional divisor, I get 0. And if I intersect exceptional divisors, I get -1 if the index is the same. So an exceptional divisor against itself is -1, otherwise it's 0. And using this pairing, I can define what is a -1 divisor, and that's supposed to generalize what's a -1 curve in P2. And that is a divisor with self-intersection -1, and that's such that the intersection with the anti-canonical divisor is 1. And that is somehow really, straight generalization of -1 curves in dimension 2, because if you replace n with 2, you will get exactly the characterization of -1 curves, blow up of the plane. And they do have the same geometrical meaning as -1 curves on the Pezzos, because if the blow up is a Mori space, so this bilinear pairing is defined in general, but now if the blow up is a Mori space, so if S, the number of points, is limited, then I have finitely many -1 divisors, and this is actually an if and only if. I have finitely many -1 divisors if and only if the blow up is a Mori space. They form a single orbit for the Weyl action. So again, the action is transitive and there's one single finite orbit, and they generate the effective cone as a semi-group, the effective cone of X. So it really is a generalization of -1 curves. But of course, in higher dimension, we don't only have divisors. We would like to be able to say what it means to be a -1 cycle in some sense of higher codimension. So this is the next definition. That's what we call Weyl cycles. So well, first of all, we say that a Weyl divisor, Weyl is not a Weyl divisor, it's not a Weyl divisor, it's a Weyl divisor. Okay, it's a bit confusing. So this is simply a -1 divisor, basically. You just rename it in order to be consistent with the following part. So a Weyl divisor is a divisor that belongs to the orbit of an exceptional divisor. So in other terms, it's a -1 divisor, according to the Mukai pairing. But then what is a Weyl cycle of dimension R? So it's a non-trivial effective cycle that is an irreducible component of the intersection of pairwise orthogonal Weyl divisors. And the orthogonality is taken with respect to the Mukai pairing. So to this intersection product between divisors that I've introduced before. So let's see a few examples and let's try to identify a few of these Weyl cycles. So let's consider P3, so three-dimensional case. I start from two Weyl divisors, so -1 divisors. These are hyperplanes, fixed hyperplanes through 3 points. I take two of them. As you see, I have different. So the first one goes through E1, E2, E3, and then E1, E2, E4. So one can compute the pairing and they are orthogonal. So one can check that they are orthogonal. And if I intersect them, if I take the intersection, well, think about it, these are two hyperplanes, they share 2 points. So what is their intersection is the line through the 2 points. So if I intersect these two divisors, I get a line through 2 points. So in other terms, a line through 2 points is a Weyl line. Also in higher dimension, it was already a -1 curve in dimension 2. So let's go up again. So increase the dimension a little bit more. So we take dimension 4, we take 3 hyperplanes, and well, they are pairwise orthogonal, 2 by 2 orthogonal. And if I intersect them all, if I intersect these 3 hyperplanes, they share 2 points and then and only 2 points. And so their intersection is clearly the line through those 2 points. But if I take the intersection of only 2 of them, the first 2, for instance, they share 3 points. So the intersection is a plane through those 3 points. So also a plane through 3 points is a Weyl cycle, etc. So in general, strict transforms of linear spans of points are Weyl cycles according to that definition. But let's take somehow a non-linear example. Let's take something curly. So we take 2 quadric cones in P3. So basically I have 6 blown up points in P3. There is a twisted cubic through 6 points of P3 that is also resolved by Castelnuovo. I have a twisted cubic, and then I take the cone over that twisted cubic with vertex, one of my points. So in this case, the vertex is the first point. So the picture here is the one on the right-hand side. So this is D. And now I do the same, but I take a different vertex. So I take vertex the second point, and this is going to be my F. And if I intersect them, so this is the intersection between 2 surfaces in 3-dimensional space, so I'm supposed to get a curve. Well, I'm supposed to get a quartic curve because I'm intersecting 2 quadric surfaces. And indeed, I get a quartic curve, but it's not irreducible. It's the union of the twisted cubic that they both contain and the line through the 2 vertices. They both contain that line. So I hope it's visible from this picture. So this intersection has two components. It has a line through 2 points, and using little h and little ei to denote somehow the class in the dual to the curve classes. And this is the twisted cubic through the 6 points. So also the twisted cubic is a Weyl curve. And somehow that generalizes the conic through 5 points of P2. So in the next, in the following part, I'm going to say I'm going to give, a list of Weyl cycles in these blow-ups that are Mori spaces. And then I'm going to somehow say what we can do with them. So what sort of questions do they answer? So now I consider the case of Pn with n plus 3 points. That was the fourth in the list of Mori spaces. So this is a list of Weyl cycles. So I have a linear span of points, like a line through 2 points, a plane through 3 points, etc. We've seen that. I have the rational normal curve of degree n through n plus 3 points. That there's a unique such curve, like the conic through 5 points in the plane, the twisted cubic through 6 points in P3, etc. So there's a unique such curve, that's a Weyl curve. The secant varieties to this curve, and these are defined, so I take the union of the T secant T minus 1 planes. So I choose T minus 1 points on the curve, I take the plane they span, and I take the union of all these guys, and then I take the Zariski closure, and that's my secant variety. That turns out to be also a Weyl cycle. And then I can take joins in between the above. So I can take joins between a secant variety to the curve and a linear cycle. So like an example is, I can take the curve itself, that would be my secant one, the curve itself, and then I can take the point, and then I take this quadricone that we've seen earlier. So this is the list of Weyl cycles. And then another observation is that they all Weyl cycles in the list of dimension r, when I fix the dimension, they all belong to the same orbit, to the same Weyl orbit of a plane, of an R plane. So they behave like divisors. They all fit in the same orbit, and there's a unique such orbit. And yeah, well, the divisorial ones, the divisorial such cycles, they generate the effective cone as a semigroup. So this really generalizes the situation in dimension 2. So this completes the picture for these spaces, and there are 2 spaces that are left over from that list. That is P3 with 7 points. This covers up to 6 points of P3, but we can blow up one more and still be a Mori space. P3 7 points and P4 8 points. These are the 2 more interesting cases somehow, because they're a little bit more complicated. So let's look at P3 7 points first. So who are the Weyl cycles? Well, we have curves and surfaces, so well, not so unexpected. So I have 28 curve classes. I have the lines. I have 21 lines through pairs of points, and then I have 7 twisted cubics through 6 points each. And then I have 126 surface classes or divisors, and they fit into these 5 types. So I have exceptional divisors. I have planes, hyperplanes through 3 points. I have quadricones over the twisted cubics, like we've seen earlier. So these 3 we have already encountered. And then I have 2 more of degree 3 and 4 with a bunch of singular points. So I have 35 cubic Cayley surfaces. These are surfaces with 4 ordinary double point singularities, and then I have another type of degree 4, sorry, 7 quartic surfaces. But for these guys, I do not have a better geometric understanding as I did have for the previous ones in terms of secant varieties, etc. So this is the full picture for P3 blown up to 7 points. And these surfaces, they generate the effective cone. Again. And the next case, which I think in my opinion is the most interesting case, is P4 blown up at 8 points. In this case, I have curves, surfaces, and divisors. So again, I have the same curves, lines and rational normal curves. I have 199 surfaces fitting in 5 different classes, 5 different types of degree. Well, I have planes through 3 points, so that like before. And then I have, this is also a cone over the rational normal quartic, somehow generalizes the cone over the twisted cubic. And so this is a cubic surface. And then I have 3 more types of degree 6, 10, and 15 that I really have to say I don't understand geometrically, but they just appear to be there in the orbit of a plane. So they form one single orbit. And finally, divisors, and I guess this is not so interesting. We have 2,160 divisors. They fit in 15 different classes. And again, I have exceptional divisors, hyperplanes, quadric cones over the rational normal curve. And this time the vertex is a line, not a point anymore. So this is a threefold. And then I have the secant variety to the rational normal curve, which we had already before. And then we have 11 more such divisors that, that I guess we don't understand so well. But together they form one single orbit and they generate the effective cone. So the behavior is always the same. So yeah, so this is the first result that we have. So now that we have classified these Weyl cycles, what do we do with them? Well, we want to reproduce Castelnuovo's result for the dimensionality of linear systems, in other terms, answering the interpolation problem. So for Pn blown up at n plus 3 points and for P3 blown up at 7 points, we show that special effect varieties, so varieties responsible for the speciality of a given system, are all and only the above Weyl cycles, the ones I've listed in the previous slides. And they contribute to the dimension formula in this way. So like in Castelnuovo's case, I have that H0 equals the Euler characteristic plus a correction term. And this time I have an alternating sum, and the sign depends on R, the dimension of the cycle itself. So the summation ranges over the Weyl cycles, and each of them contributes by this number, and that really generalizes the situation in dimension 2. So this is the multiplicity of containment in the base locus, which is to be computed, and yeah, it's not so obvious, but somehow we were able to compute it. So there is one open case, as I mentioned earlier, P4 blown up at 8 points, but yeah, I'm confident that this can be solved. And yeah, so this is about dimensionality, and then the last thing that I would like to mention is that they also, so these Weyl cycles belonging to these single orbits, there is one orbit per dimension, they are also responsible for the birational geometry of these monodromy spaces. They explain completely they explain the effective cone. In fact, the divisorial ones, they are the extreme arrays. They span the extreme arrays. But they also give a description of the movable cone, which is also finitely generated polyhedral and rational for Mori spaces, and also the Mori chamber decomposition of the effective and the movable cone. So before I give you the result, I will maybe take a couple of minutes to look at one example in detail, so at least we know what we're talking about. So I'm going to take the blow up of Pn in 2 points, so at least I can draw the Néron-Severi space is three-dimensional. The effective cone is triangular, so I'm going to draw it like this. So this is, well, a section of the effective cone. It's a 3D cone. The extremal rays are the two exceptional divisors E1 and E2, and the class of a hyperplane through 2 points. So these are Weyl divisors. This one is a Weyl divisor if n is 2, otherwise it is not, because it is movable. And then I have this Mori chamber decomposition. I have a decomposition in triangles like this. So this is the class of H minus E2, H minus E1, that's completely symmetric. And this is the class of H, a general hyperplane. And what we can say is that the movable cone is this square. It's the unit of these two triangles. So this is movable cone of X. And there is the movable cone is it has a two-chamber decomposition. So there is this wall. So this one here, the triangle in the middle is the net cone of X, and then the chamber, the adjacent chamber, is obtained. Well, the crossing of this wall is described by the flip. So I can consider the flip of X along the line through 2 points, and there is a unique line through the 2 points. And somehow what I want to say is that the Mori chamber decomposition of the effective and of the movable cone is induced by a hyperplane arrangement in some sense, in the sense that I have only 3 hyperplanes. I'm gonna, So these 3, I have these 3 hyperplanes. So they correspond to 3 curve classes, and each of them correspond to a Weyl cycle. So this corresponds to E2 as a Weyl cycle. This corresponds to E1, and the red one that I've already observed corresponds to the line. So I have 3 Weyl cycles, the line and the 2 exceptional divisors, and they are in correspondence with the hyperplanes cutting out the Mori chamber decomposition of the effective cone of this Mori space. And this is true in general. And this is the result in general. So I'm gonna simply generalize what I've just explained in the previous slide. So if I take the blow up of Pn an S point, which is a Mori space, if I take a W of a Weyl cycle, I can compute the multiplicity of containment of W in the base locus of D, that I also need for the previous formulas. And that is computed simply by intersecting D with a curve class gamma that depends on W. And this curve class gamma is a curve class that sweeps out V. It means that if I take the reducible elements with that class, they cover a Zariski open subset of W. And the interesting fact is that there is a unique such class. So for every Weyl cycle, there is only one curve class that sweeps it out. And each such, so intersecting with this curve gives me an integer. If I take the negative, I get the multiplicity of containment. And the second result is that if I consider all the hyperplanes in the Néron-Severi space obtained by intersecting with these curve classes for all the Weyl cycles, together with setting to 0 the multiplicity of the exceptional divisors, this is a hyperplane arrangement in the Néron-Severi space. It's completely determined by the classification of Weyl cycles, and it induces the Mori chamber decomposition of the effective and movable cone, and also what we may call the stable base locus decomposition, which is usually a coarser decomposition than the Mori chamber decomposition. So stable base locus chambers are chambers where all divisors in there, they have the same stable base locus basically. And in other terms, we are saying that stable base locus is a union of Weyl cycles in this case. And that is all I wanted to say. Thank you.